Okay, this is Dr. Williamson helping you out with the second part of the lab. What you're going to do is you're going to get a 10 mil graduated cylinder and you're going to weigh it when it's empty. Then you're going to add 2 to 3 grams of urea into it. And you're going to accurately reweigh the graduated cylinder combination with the urea. So you know exactly how many grams of urea are in it. It should be between 2 to 3 grams. And you know exactly how much that is that's in there. And then what you're going to do is you're going to slowly add water to it and drop by drop until you find exactly the minimum amount of water needed to just barely dissolve all of the urea that you added into the graduated cylinder. Okay, remember this video is meant to be a supplement to reading the instructions, not a replacement to reading the instructions. Okay, once you have done that, you'll be able to calculate the equilibrium constant between the urea and the water, where the equilibrium constant will be the concentration of urea that's in here divided by the fraction of the water that's in here. Normally, we don't include water liquid in the equilibrium constant because it is in large excess. The concentration of the water is in large excess, so its concentration doesn't change. However, here, this water will not be in large excess compared to the urea, so we have to include it. So it's included as the fraction of the water, okay? And that's going to be calculated as the concentration of the water in this urea mixture divided by the concentration of pure water. And I've told you guys several times what the concentration of pure water is. So you're going to have to look in your notes what that is. The concentration of the water in the urea will be equal to the moles of the water, right? If you know the grams of the water that you added, because you're going to weigh this afterwards, if you know the grams of the water that you added, you can convert the grams of water into moles of water. And if you read the volume here, remember it goes to 2 decimal places. If you've got the moles or millimoles, because you have the milligrams, either way, you can divide it by the milliliters, or you can divide the moles by the liters. If you do either way, the millimoles divided by the milliliters, or the moles divided by the liters, either way, that will give you the concentration of the water in this urea solution. And you know the concentration of pure water, you can divide those two. That value of F will go right up in there. You divide that by the concentration of the urea, because you know the grams of urea, you know the molar mass, you know the volume that the two are mixed in, right? Because you're going to read the volume. Remember, it goes to 2 decimal places, and then you can get the equilibrium constant. Then you will calculate the value of the Gibbs free energy, where delta G naught, standard state Gibbs free energy, is equal to minus RT natural log of K. The value of R is given in your lab manual or your lab instructions. And then from that, you're going to have delta G naught is equal to delta H naught minus T delta S naught. That's supposed to be an S, does not look like an S. On my planet, it means hope, but on this planet, it's an S, okay? So you're going to get this part. Let's see here if I can do a shape. I want to do a shape. And I'll do it in, that's a good color. So you're going to get this part from today's lab. You got this part from part A. So then you will calculate delta S for the final part of the lab. And you'll have to assume the correct, you'll have to read the lab instructions to get the correct temperature that we're using. Okay, I hope that helps. And, that's all for now.